Welcome back. We'll have a lecture 16 tonight, which is bandwidth of FM signals. We learned last time that it was just sort of a mess to get it right. Now, I owe you the results of a poll that we took over the internet over the last couple of days. The question was exactly what day our exam would be on. And I looked over the answers, and there was also some discussions and emails as well. And so I'm going to stick with the way things are, which I know that a couple of you that'll make unhappy, but I got the sense that for more of you that would be fine. And then for the vast majority, nobody really cared. So I'm going to say that we're going to have it Monday, April 14th, just like I said last time, and it will cover the material up through the end of last class. Up to the end of last class, which is really basically section 5.1 in the book. Maybe a touch more than that. All of chapter 4. The homework problem will come from chapter 4. It'll be closed notes, closed book, no calculator. Okay? Questions, comments, worries, gripes, complaints, hisses, cheers of delight? Nothing.
Yeah.
Oh, all right. Let's not get too rowdy. Okay. So let's back to FM. Let's do a little bit of review, just so we kind of hit the ground running on things. Now, with a lot about this course has centered around a carrier frequency, in case you haven't noticed. We like local oscillators. We like local oscillators at very high frequencies that propagate through by electromagnetics, for example, off of an antenna through a fiber optic cable. And so a lot of what we have to do is we're stapling or mixing or combining a message signal with that carrier frequency. And for amplitude modulation, the amplitude of that signal contains the information. For the exponential or the angle modulation, what goes on in here carries the information. What goes on inside of that carries the information. For example, well, do the easier one first. For example, if we are talking about phase modulation, then the phase angle that hangs off of the end of this carrier, the phase angle here contains that message signal. So MFT is our message signal. KP is a scaling factor. Just a design, think of it as a gain amplifier if you want. So MFT is our message signal. KP is our scaling factor. And somehow we have to work to figure out how to put it inside the cosine, inside the payload of the cosine. Okay? And so this is the example of phase modulation. And similarly, there's also the example of frequency modulation. Both of these are angle or exponential modulation. Okay? And the form of that signal How legible is that? Not very. I'll talk you through it. So for the FM signal, I have A cosine of omega CT. There's my carrier frequency. My message signal now I'm wrapping in an integral first. I'm low-pass filtering. I'm averaging. I'm low-pass filtering my message signal. So I'm integrating it. And then I'm multiplying it by my scaling factor, K sub F. Okay? So if I compare the phase modulation and the frequency modulation, I have almost the same form, except what I do to precondition my message signal is a little bit different. Here I just plop it in. Here I integrate it first. Okay? Now, there is one thing that's very, very important that we always consider, and that is the instantaneous frequency. So, in both of these situations, the frequency is changing as a function of time. The precise frequency is changing as a function of time. Anytime I have a complicated theta of t, I have a complicated frequency dependence. So if this term wasn't here, I'd just have omega ct. But now I've got this m of t in here, and so all bets are off. Whatever m of t here drives what my frequency is, what my instantaneous frequency is. And so does anyone remember the definition of what the instantaneous frequency is? Or is it not the definition, how to calculate it? Good. It's whatever stuff is inside that cosine, whatever stuff is in there, all right, stuff. Okay, whatever stuff is in those brackets, then what we want to do is we want to take d by dt of that stuff. And I guess I have to be formal and use Greek letters, so I'll use d theta dt. Okay? So that's the and what I want you to do is sort of start to get in the habit of saying, okay, how do I calculate? How do I deal with this cosine, which with a very, very funny payload? If I do this here, if I take d by dt of the stuff that's in here, I get omega c from that term, and I undo the derivative, I undo the integral, and so the instantaneous frequency, which is as a function of time, is omega c plus kf times m of t. So that's my instantaneous frequency for my FM signal. And my instantaneous frequency for my phase modulated signal, also a function of time. Take the derivative of this term here, I get omega c. Take the derivative of this term here, I get kp times the derivative of my message signal. Okay. So in both situations, the m of t drives what my instantaneous frequency is. Okay. Let's take a look at the FM signal. The bigger m of t is, the bigger my instantaneous frequency is. The smaller my m of t is, the smaller my instantaneous frequency is. In other words, the amplitude of m of t, the amplitude of the message signal, scales the instantaneous frequency. The louder this message signal is, the bigger this message signal is, the more I have, the higher the frequency component it is. Okay? And so if I ask the question, what's the bandwidth of my FM signal? The excursion of m of t defines the excursion of the instantaneous frequency. The excursion, what m of t does, defines what the excursion of the instantaneous frequency is. So I'm going to take a look at m of t. You're going to take a look at M of t. And I don't know much about M of t, although I can postulate a few things. One of the things that I'll know is that M of omega, actually let me write M of f, has a frequency of b. Okay? So the natural frequency in hertz, the biggest value of M of f is capital B. Okay? Let me just sketch. It's random. It's a random signal. But I'll have some kind of sketch that looks like that. Okay? Your voice goes higher, then lower, and so on, and sketches out. And in this case, I'm going to have it so that it goes both negative and positive. Okay? Now, I can break this guy up into finite pieces. And so let me start to do that. I have to be a little careful on exactly how wide to make these pieces. I can make them really big, but then I lose information. If I make them really small, then I'm just over sampling. Put it that way.
Is that adjusting your carrier frequency, like the width of those?
I've said nothing about my carrier frequency. What I'm plotting here is M of t.
No, I mean the chunks, the width of the samples.
I understand. I've said absolutely nothing about what my carrier frequency is. So I know that's a little counterintuitive, but just look, take a look at what's on the paper. Okay, I'm starting with my message signal M of t. Eventually, and this is where you're going. Eventually, I'm going to look at what omega sub c is. But what I'm looking at here is what's going on right in this case here. Okay. So there's 1, 2, 3 terms of it, and I'm going to start by looking at what M of t is. And by the way, what I want to know is what's the bandwidth of the FM signal. That's the goal of this discussion. So the question we have is, how wide should those samples be? We're starting to talk about sampling. We're starting to talk about how fast we want to collect information. Single pieces of information. You're right, sampled, discrete. What we want to do is we want to make sure that anything fast on that signal isn't left behind. And fast happens here at B, at capital B. Okay? So the high frequency stuff here is out towards here. The low frequency stuff is anywhere in there. So we want to sample at 1 over 2b. And that's equal to t, and that is in fact called Nyquist sampling. And today I'm hand waving it. Today how many of you have heard Nyquist sampling? How many of you know that you have to sample a signal twice the bandwidth, at twice its bandwidth? Very good. So most people have heard of it, and almost everybody knows the mathematics behind it too. That's excellent. Do you know why? Pardon?
To avoid aliasing.
To avoid aliasing. Do you know what aliasing is?
It's in the spectral density. It's where they overlap.
Things start to overlap. I want to go through that carefully with you. I won't do that today. But when we go into pulse code modulation and we do sampling carefully, I'm going to do a demonstration of Nyquist, a construction of Nyquist, and so we'll be on very, very firm ground there.
Is it? I think I heard someone the exact Nyquist sampling rate of 2 times the bandwidth is actually, like, if it accidentally samples.
Yeah. So the question is pushing me on the details of the Nyquist sampling, whether or not it has to be exactly 2 or greater than 2, and so on. It does have to be slightly greater than 2. You don't want these things to just touch. You want them to have some guard band. From a theoretical perspective as well as an experimental perspective. But let me table all that for maybe about a couple of weeks, and then we'll come back and we'll do that rather carefully, and you'll own it. So today let's just rely on the fact that we know a rule of thumb. A good rule of thumb is a Nyquist and its sampling. And again, I'm going to argue it today by just saying, hey, what's happening out here is the highest frequency content, and as long as my pulse of sampling is on that order, I'm doing great justice to everything down here, and I'm catching the important part of that last little tail of the signal. So taking time, and 1 over time gives me 1 over 2b times t. Now you can see why I'm working in natural Hertz units, because it gets me nice seconds out of this. I don't have to mess around with radians and stuff like that, which is no big deal, but makes it muddy a little bit. Okay? Now, let's see. I'll go to some arbitrary point, and I want to pick one rather carefully. I'll just do this one here. And this one, I don't know where you want to call it, but I'll just say that that's at interval t sub k. That's at interval t sub k. And so if you think about my notation, m of t at this point here will be m of t sub k. That's the value. This is a piercing glimpse into the obvious. M of t, m is equal to m of t. What is m of t of k? It's m of t of k. Okay, so it's nothing really amazing about that. So, but then it stands to reason. Well, my instantaneous frequency is equal to the carrier frequency, omega c. Somebody wanted to get that in there, and I'm doing it. Plus the scale factor kf multiplied by m of t. So, if my instantaneous frequency is that, then the instantaneous frequency at some arbitrary point t sub k, well, that's going to be the carrier frequency plus kf times whatever the value, whatever the single value is for m of t at t equals tk. Again, that's another piercing glimpse into the obvious. Right? Although what I've done is I've said that my instantaneous frequency is the same from that point to that point. After sampling. So I've lost a little bit of information there. Not much, but a little bit. Okay? And it holds this frequency for t equals 1 over 2b. Now, if I Fourier transform just this little cell here, just this little rectangle, if I Fourier transform just that rectangle, there's my cell, there's my little cell. If I Fourier transform this, I'm going to be left with a sinc function. And yeah, okay. So sorry. So what I'm doing is I'm taking this little square. I'm taking this little square here, and I'm putting it into here. And then I'm asking what that looks like, and it's going to look like a sinc function, and it's going to be centered at the instantaneous frequency of the signal. The distance from there to there goes as 1 over capital T. In this case, it's 4 pi b. Don't worry too much about the constants. They'll all come out. And so this particular point in frequency space is omega c plus kf m of tk plus 4 pi b. And this particular point here is omega c plus kf m of tk, that's my center line, minus 4 pi b. Okay? So my instantaneous frequency holds for a certain length of time. If all I care about is what's going on in the frequency content there, then this is what I have. The longer I hold, the tighter the sinc function is, and the more stable the instantaneous frequency is. Okay? The faster m of t moves, the faster the instantaneous frequency moves, and the fatter this guy is. Okay? All right, this is all about some arbitrary t sub k. It's just an arbitrary little cell there. But what I really care about is the bandwidth, the overall bandwidth of the FM signal. And so if I think about this, however big m of t is, then the instantaneous frequency will be bigger. So this instantaneous frequency is going to roll up and down, depending on what my message signal is doing. But it seems to me that if I have a max and a min, the fastest instantaneous frequency is going to be when I'm at a max, and the slowest is going to be when I'm at a min. If my message signal never goes below this bar and never goes below this bar, then my frequency is never going to be higher than the frequency that it is here or lower than the frequency that it is here. Okay? So what I'll do is I'll call this m sub p, and I'll call this minus m sub p. Yes?
So you said the frequency is the highest at the max?
The instantaneous frequency,
Okay.
the instantaneous frequency here is going to be highest when m of t is maximum. And it's going to be lowest when m of t is minimum. Okay? You see that? Because the magnitude of this guy is kicking the instantaneous frequency up or down. Okay? All right, so now what I've done is I've said, okay, I have an absolute maximum MP and an absolute maximum minus MP. And maybe I can actually arrange that to realize that. Maybe I can actually put a limiter, so you will not go above plus or minus 12 volts because that's my bias on my op amp. That's a pretty easy way to making a limiter, right? It's going to clip it and it's going to cause distortions, but it's not going to change this frequency. Okay. Well, if that's the case, so notice that I'm making this symmetric. That I'm using the same MP on the top as on the bottom. Okay. So there's no DC value on this signal. I've stripped away the DC value. Okay, it's a double-sided 0 DC. So I have a blocking cap in there. Okay. Well, the max frequency, and what I mean by that is the instantaneous frequency. And that's equal to omega C plus KF MP. So where's my sync function? Here. Okay, here's my sync function. And so what I've done is I've slid my window around until this guy here is max. And then my center is max. But I still have a little bit more information I have to take care of. Does everyone see where I get that 4 pi b in there? The maximum frequency that I want to consider is going to be the maximum of the sync function at the peak, plus a little bit more because my sync function is fat. Okay? The minimum instantaneous frequency is equal to omega C, and that's when we're down in this guy here. We have a little railroad car there, a little box car there. So it's minus M of P times KF. That gets me to the center of my sync function, but now I want to take it a little bit south. A little bit on the south side. For my guard band, or for my little bit extra information. Okay. Well, here's the maximum frequency excursion. Here's the minimum frequency excursion. And we got there primarily just by thinking about what the instantaneous frequency is doing with respect to M. And then remembering a little bit about our Fourier transform tricks. And it seems to me if that's my max and that's my min, the bandwidth of the FM is going to be cancel 2kF, just subtract the 2kF MP. Subtract the 2 again, and that's 8 pi times B. That better? Sorry. I watch on the back monitor, but it's not as easy to see as that. Oh. Plus in there, right? And the units of this is radians per second, right? The units of that is radians per second. I've got pies floating around in there for crying out loud. Okay? Any questions about that? Any questions about the construction? Want me to review the high points?
Yep.
Figured. High point number 1, I have a message signal. Message signal goes between minus MP and positive MP. Okay? High point number 2, the message signal has a bandwidth, capital B, which means I can Nyquist sample it into little boxes, little boxcars, with a width, capital T, that's 1 over 2B. High point number 3, the instantaneous frequency for my FM signal is omega C plus kf times m of t. The magnitude of m of t drives what my instantaneous frequency is. So if I'm at MP, if I'm at MP, I have a maximum instantaneous frequency of omega C plus kf mp. If I'm at the minimum, it's omega instantaneous of omega C plus kf minus kf mp. But that's not completely true. Not exactly true, because I'm holding my point for a duration of 1 over 2b, which means I have an uncertainty in my frequency that is a sinc function. And the sinc function has a width. So, when I go to calculate my maximum instantaneous frequency, yes, it's proportional to omega c. Yes, it's proportional to you add in the kf times mp, but then you also add in a small amount more that takes into account the bandwidth of the sample, the bandwidth of the message signal itself. Okay, the bandwidth of the message signal itself. Yes, sir.
When you combine the two to find the max swing of the frequency,
this is the total bandwidth of the FM signal, right?
It's 2 if you're doubling MP, but the MP and the minus MP could be different, right?
Oh. So
you take the greater of the two, I guess.
Well, no. Okay. Hang on. I'm doing it. So the question is, what about this MP? Well, what I'm saying is, I'm saying that I have a double-sided signal. I have an AC coupled signal. And so, in the example that I'm doing, I'm stripping away my DC, and in that case, I'm always going to have the rest of the terms of my Fourier series are always going to give me a maximum MP and the same symmetric minus MP. Okay? If I don't have that, then I will have a DC offset. If I do not have that, then by definition I'll have a DC offset, right?
Okay, I see.
If I do have a DC offset, that's okay. You're absolutely right. I'll have an I'll have an MP positive and I'll have an MP negative. And this MP will now be, instead of 2 MP, which, let's face it, is just the difference between there and there, the distance between there and there.
Yeah.
If now I futz with this and I move it up or down, I have to take MP positive minus MP negative. I have to take the spread of that. Okay? So yeah, that's a small generalization on what I'm doing. Okay? But I'm trying to get it into a format that's almost, but not quite a famous result. Okay? All right, so let's do a couple of things. The bandwidth for the FM signal. And I want it in hertz, not in radians per second. So all I do there is I divide this by 2 pi. And notice what I've done is I'm going to define delta F as KFMP over 2 pi. So that's the range of the frequency around the carrier. That's the bandwidth of the frequency of the instantaneous frequency around the carrier due to the message signal amplitude m sub p, and due to my scaling factor k sub f. So whatever I choose kf is, whatever I choose, whatever mp is, I multiply them together, and that's the spread of the peak of the sync functions as they wiggle around. Then I add in an additional bandwidth to account for the signal itself. An additional bandwidth to account for the signal itself. And that's what this guy is here. So this guy could be fairly large, and this guy could be moderate, depending on what k sub f is. Okay? Well, let me go ahead and factor out a 2b. So I'll factor out a 2. That gives a 2. Then I'll factor out a b. That means I pull this and I have to divide that one by capital B. And this is nice because this gives me a dimensionless number. Hertz over hertz. The hertz of the top of the sync function normalized, the wiggle of the sync function normalized to the bandwidth of my signal. Normalized to the bandwidth of my signal. And I'll call that ratio delta F over B. I'll call that a deviation ratio, and that's equal to delta F over B. So that's just beta. I'm just calling that beta. So this factor of 2 here, this factor of 2 here, comes from the fact that I'm looking at my single sideband of my message signal. Just my half frequency content of my message signal. So I've got to double that once I modulate it. Okay? So that factor of 2 says that instead of dealing the single-sided capital B, I'm now double-sided. Okay? Not unlike double-sided AM DSB. Double sideband AM DSB. So I've got an extra factor of 2 in there. This factor of 2 comes from exactly where I cut off my sync function. Exactly where I decide to truncate my sync function. I could have spread it out over here, and that number would have gone up. I could have started to crowd it in close here, and that number would have gone down. So the rather arbitrary decision that I made on truncating this, on defining what the width of the sync function is, very arbitrary, but I happen to choose that 4 pi b, and that 4 pi b, when all the dust clears, gives me a factor of 2 there. Okay? And the reason I bring this up is, in the book, you'll see exactly the same formula, but there'll be a beta plus 1 there. There'll be a beta plus 1, which is a nicer thing to memorize, I think. Okay? And I'm not too stressed about which one you use in practice. Okay?
I mean, they divided out another 2.
What they did was instead of truncating the sync function here, they truncated it a little bit up to here. Well, I'm missing information too. Look at all these wiggles out here. Yeah. But I'm not, listen, I'm not proud of what I'm doing either. I'm not going to slam them because I'm missing all these wiggles out here. Okay? Don't worry, we're going to look at this a couple more ways. We're going to get comfortable with that. Okay? But so what I'm saying is, this number here, we made that number happen. That too, we made it happen by where we set the width of our sinc function. Okay? Anyway, this is called Carson's rule. Okay? And Carson was a big name theoretician at Columbia back in the early part of the 1900s, 1910, 1920. Yes, exactly around the time Armstrong was working. In fact, Carson, when Armstrong was starting to think about this frequency modulation business, Carson was the guy that came out and showed that definitively, but according to his theory, that it would have horrible performance and not worth doing, and basically was infeasible. After Armstrong demonstrated it and showed that it was really brilliant, and it took away the hiss, static, on the channel, and it was very low noise, Carson sort of scratched his head and came up with a theory, and this is one of his results. So the same thing that he said couldn't be done, he then said, okay, well, now that it can be done, now that an experimentalist has shown that it can be done, I guess there's got to be a good theory for it, and I guess I should write it. Theoreticians are wonderful that way. They'll tell you they can't do something until you show them how to do it, and then they'll show you why you just did what you did. Cynic. I'm a cynic. I'm also experimentalist. So that's part of that. And that's not strictly true. That's a very bad statement to make, because theory does, in fact, guide you to what you want to do. In this case, we can lord it over Carson because he was wrong, but good to Carson, he got it right at the end. So anyway, when we talk about Carson's rule, and people do, and they should, it's a great rule. When you talk about Carson's rule, what you're saying is you're estimating the bandwidth of your FM signal while it's in the channel. And that's huge because what you want to do is you want to make bandpass filters, to segment off your information from somebody else's. Oh, heck, you've got two FM stations that are in the same market. How close together can they be without interfering? You need to know the bandwidth that each one uses, right? AM, it's trivial. If you've got an AM signal, you know trivially what the sideband widths are. FM, it's much more subtle, because you generate all the harmonics of the Taylor series that we looked at last time. All the Taylor series of the A squared, A cubed, A to the fourth, all those generate higher harmonics. Where do you know when to stop? Is it true that you can have only one FM station in a market? That would be horrible. Not worth the trouble. So this is a way of saying, no, it has a finite frequency space. The estimate is this way, and you can now space your FM signals apart, your FM radio stations apart, by this much plus a little bit of a guard band. Plus that much plus a little bit of a guard band. So tremendously useful formula. Tremendously useful formula, and the one that we came up with just by a couple of very, very simple tenets. Okay? Now, let's ask the question again. Let's ask the question again and say, what is my bandwidth for my FM signal? But now what I want to do is I don't want an M of t with a Fourier transform of capital M of omega. What I want is just a single frequency, a test signal, if you will. Just a single tone test signal for that. So my M of t will equal some alpha, some strength, times a single frequency of my Fourier series. Now, do you remember our A of t was the integral? That gives me my phase excursion. And if you remember what we were doing last time, we wrote down what the FM signal was in terms of this A of t, in terms of the integral of the message signal. And so now we have a very simple message signal. We can go ahead and put this in. And so this is my A cosine of omega ct plus kf times my phase term, the integral of the M of t. Okay? So, where was I? Fm is equal to A cosine of omega ct plus kf times the integral. This guy here is A of t. The integral of my cosine is that sign there. Okay? Let me write this a little bit differently. A e to the j omega ct, that's nothing scary about that. E to the j, okay. Here's kf times alpha divided by omega m. Anyone recognize that?
Is that the deviation?
That's what I call it. You're right. Is it the deviation ratio? That would be beta. Is that what I called it? Is that beta? Let's compare. See if we're there. Beta is delta F over B. Delta F is KF times MP. MP is the peak of my signal. So I have a KF in there, so that looks good. MP, well, look at that. I have an alpha instead of an MP. So that looks good so far. I've got a 2 pi in there, and that's 2 pi times capital B. 2 pi times capital B. Well, gee, what's capital B for that? Or what's 2 pi times capital B for that signal? Why? Why is it omega m? So it only goes out. Here's how I defined capital B. For this particular case, for this tone modulation in hertz, there's F sub m, omega sub m over 2 pi. So if there's nothing to the north of that, that's the limit of my bandwidth. So 2 pi times that modulation frequency, that's absolutely my deviation ratio beta. Absolutely my deviation ratio beta. Pretty, isn't it? I like the fact that there's not a factor of 2 or 7 or anything like that in there. It's just falls out nicely as a beta. Okay. Now here's my nice formula for my FM signal for a single tone, for a tone message signal, a single note that I send out. Remember, all these guys are sines and cosines, right? So this is cosine of omega ct plus j sine of omega ct. Here's a cosine of beta sine omega mt plus j sine of beta sine of omega mt. Okay? Do you remember the extra credit problem on the exam? I had a cosine of a cosine. So this is where that comes from. This is a cosine of a cosine, and it gives you conniptions. Okay. Now it's periodic, right? Because I can find a capital T such that the sine of omega, the cosine of the sine of omega mt plus capital T is equal to the cosine of the sine of the omega m of t. So it is a periodic function. But other than that, it's really nasty. It's really, really poorly behaved. And in fact, whenever you see a cosine of a cosine, of that variable t, you're going to get something called Bessel functions. Okay? You're going to get something called Bessel functions. Now, it's let's see. How many of you have heard of Bessel functions? A handful of you. How many of you worked with the Bessel functions? Maybe just, oh, wow, that's good. Once or twice in differential equations. That means you must have been looking at very interesting differential equations. Non-constant coefficient differential equations. Cylindrical coordinates, probably. Partial differential equations is my guess. So yeah, so it comes up. It used to be, so Bessel functions, so you know sines and cosines come up a lot, and they're solutions to differential equations, and they come in from triangles, and they come in from a lot of different things. And so as an engineer, today, you see sines and cosines come up, you expect them, because they come up in all other walks of life. They come up with all classes that we have. Even if you head over into mechanical engineering, you're going to run across sines and cosines as solutions to a huge array of problems. And after a while, you forget that a sine and a cosine is a transcendental function, and that if you really want to know the answer to what a cosine of something is, you've got to pick up your calculator and enter in the argument and press the button for the cosine. Well, in the old days, because we didn't have calculators and computers, the Bessel functions came up an awful lot in a lot of different problems. And so electrical engineers in particular got to be comfortable by seeing Bessel functions. So it's just another transcendental function, one that you painstakingly learn to get familiar with. And there's scores of transcendental functions out there, and depending on what problems you work on, you'll become more or less familiar with certain ones. Bessel functions are one of those that we don't see that often. And one thing I would point out to you is it's ridiculously simple to work with Bessel functions nowadays, because your calculators have Bessel function keys on them. Well, if your calculator doesn't, if your TI calculator doesn't, I'm sure there's a way of programming it to get it there. But your Excel spreadsheet does, your MATLAB does, Mathematica does. And so what you might do is you might spend a little bit of time plotting a few of the Bessel functions just to get familiar with them. And I'll show you some plots before too long. I'll show you some plots of what Bessel functions look like, so you get some idea of them. So plotting them, that's a good start. And just get familiar with them. Of course, then being greedy, what I'd say is if you have it plotted, you might as well take the Fourier transform of it and see the fast Fourier transform and see what that gives you. That's kind of scary. We won't push that too hard. But what I'm saying is you can build up a familiarity with Bessel functions very quickly now, if you want to.
So you're saying that's the cosine of cosine or cosine of sine?
Both of them will give you Bessel functions. It's the concept.
What we have here is the cosine of sine.
Well, you have a cosine of beta sine of omega mt plus j times the sine of beta sine t. And you multiply that by a cosine of omega ct plus j sine of omega ct. So you have to multiply these out, and what you'll get, even if you take the real part, is you'll get one term and then another term. Okay? What you should do is leave a little space and use Euler's relationship and see where that takes you. But let's take a little digression into a little bit of Bessel functions, a little bit of what we're doing. And I have this e to the j beta sine of omega mt. And I can write this as a Fourier series. I know that. And I don't know, since I have an omega m floating around in there, I might as well make my Fourier series with the kernel of omega m of t. Of course, with a little bit of effort, with a couple lines, 2 or 3 lines, if you can show that this is periodic in omega m with a period of 2 pi over omega m. Whatever value I have here will come back to the same value when the sine comes back to its point. Sine will go to 1 at omega m t equal to what? Pi over 2 plus 5 pi over 2 plus 7 pi over 2 and so on. Okay? So this will always cycle back and forth. This will always cycle through the same value. So for that reason, this is periodic, and I might as well pick my Fourier series. Okay. Now notice I need to figure out what C sub n is. And it turns out, I won't do this for you. Turns out that the coefficients of that Fourier series, coefficients of that Fourier series, is given by the Bessel functions. The Bessel function of beta, this factor here, which is our deviation ratio. So there is a J0, a J1, a J2, a J3, a J4, a J5, a J6, a J27, a J minus 27. And what you would do is you would go to your Excel spreadsheet, and if you want to know the number to put into that Fourier series, you would take your deviation ratio, let's say 6, and you would say that means your bandwidth is 6 times the natural bandwidth of your message signal. And you would say, what is J0 of 6? What is J1 of 6? What is J2 of 6? What is J3 of 6? What is J4 of 6? And what you'd find is some interesting behavior that generally over the long run, this is going to get smaller and smaller and smaller, but it'll wiggle around. It'll oscillate around a little bit. Okay? Go up a bit, down a bit, up a bit, down a bit. So this Fourier series will converge. Question is, how many of these do you need to adequately track your signal? And I'll tell you that in a little bit as well. Yes?
You mentioned that the ratio is the multiple of the bandwidth in that equation.
Okay, the ratio is the multiple of the bandwidth. Okay.
Is it something where it's
Sure. So here's my beta.
right.
My beta is the ratio of the amplitude to the fundamental it's the amplitude to the fundamental of the frequency. But we had a better formula, I thought, which was this beta was the deviation ratio, which was the delta f, that was the spread of my instantaneous frequency, the peak of my sinc function, divided by the width of my sinc function, which is basically my baseband bandwidth of my message signal. So what the swing of the peak of the instantaneous frequency divided by the message signal, that's my deviation ratio.
The one-sided bandwidth?
That's the way I defined it. And that's why you get a 2 out here. I defined it as half bandwidth, and I get a factor of 2 out here. Some people will define it as a full bandwidth, and there goes your factor of 2. So I'm not trying to be funny, or I'm just trying to be explicit so that you recognize that people do different things when they set up a problem. Okay? You will too. It's okay. Just be clear about what you're doing. All right. Well, let's go back to this guy here, and then I can write so now. If I take this guy here and I multiply through, I just tack on the carrier frequency to all my harmonics of my modulation tone. So my modulation tone has all these harmonics, n harmonics, and they're just centered around my omega c. Exactly what we saw with the modulation property weeks and weeks and weeks ago. And so we'll take just the real part of it to give me my real signal. And there's my cosine series. There's my cosine series for my tone modulation, the FM signal of my tone modulation.
Is there no A anymore?
What does A tell me? What did I do last time with my A? Power. It's the power of the signal that I transmit. It's always the same, regardless of what M of T is, for an FM signal. So that's what that A is doing. It's just scaling the power. So, we start with a message signal that's just a single tone. It's just a single tone. When we do FM modulation on it, when we have the FM signal, it's an infinite sidebands. We've generated infinite sidebands. An infinite number of sidebands. The strength of the nth sideband goes as the nth Bessel function of beta. So as n gets bigger, j of beta Jn of beta will go smaller and smaller, but not monotonically and not smoothly. It'll wiggle around a little bit. So you have to figure out exactly how many of these terms to get so that you keep most of the power of your signal. And I'll do an example of that, but not today because I'm running out of time. So if this is decaying, it gets smaller eventually. Okay? We can set a rule we can ask the question, when does that J sub n of beta become negligible? And some say this happens for n greater than beta plus 1. Remember, we're taking J of beta. And so when n is bigger than beta, when n is bigger than beta, if beta is 6, then when n is 7, 8, 9, it gets very small. If beta is 12, then n equals 12, 13, 14, 15, we start to get small. So people who work with Bessel functions, some would say that for n greater than beta plus 1, J sub n becomes beta. So the number of significant sidebands is beta plus 1. The bandwidth will equal the number of sidebands that I keep. The bandwidth will be proportional to the number of sidebands that I keep, and it will be minus and plus sidebands. So twice times the number of n that I keep, the number of sideband, the number of harmonics that I keep, times the width of each of those harmonics, f sub n. If I substitute in for n the number of harmonics that I want to keep according to this rule, I have Carson's rule again. I have Carson's rule again. And you can see why there's some fuzziness here. I've got an infinite summation, and someone who wants to keep a little bit more information might say, okay, n must be greater than beta plus 2. Just has to be a little more cautious, spending a little bit more bandwidth to keep a little bit more signal. Well, then the number of significant sidebands is now beta plus 2. And then this guy goes to twice beta plus 2 times Fm. So it depends where you cut off. Your judgment, it depends what your judgment is of what you call negligible or what you call where you cut things off. Okay? Judgment requirements, specs. All these things play. Fidelity. How good a signal do you want? If there's no noise, you want to keep as many harmonics as you can discern. Okay. Let's see. Okay, good. Let me try something here for just a sec. Desktop. Okay. Yes. So I just want to sort of walk you through this. Here's my. This is all from my website. I just hope you still go there. It has some interesting things on it. What I plotted here are the first three Bessel functions: J0, J1, and J2. The blue is J0, the red is J1, and the green is J2. Notice that J0, 0 is even. So J0 is even. J2 is also even. J1, 1 is odd. That's an odd function. Okay. So parity, the Bessel functions have parity. Really nice rule. They have parity, and the parity follows their index. So you see that the J0 starts high, it goes down, and it oscillates. It'll oscillate, it'll ring down. Almost like a sinc function, except not quite, because if you look carefully, and you should, the peaks and the zero crossings change. They get wider out. The peak-to-peak distance from there to there gets wider as you move out away. So it rings, but the frequency changes as it goes out. That's not the same as the sinc function. Okay? And the same could be said for the red. It's this decay that you're now looking at. Okay? So this is what the Bessel functions look like. Here's the choice that you're making with that n+1 versus n+2. I've plotted these guys, and I've actually plotted n versus jn of beta. What's plotted here is actually jn of beta as a function of n, and you see that for the beta equals 1, the beta equals 2, the beta equals 3, those are my deviation ratios. You see where these things start to fall down, where they start to become negligible. And the red dots are the n+1 dots. The blue dots are the n+2. So Carson's original rule, as Lottie is doing it, is calling a negligible at this line here, and the extra by keeping a little bit more, you're keeping a little, you're making it a tighter judgment. Okay. So which one's right? Neither is right. But this is the rationale. Some people will say the red is good enough. Some people will say even the blue is not good enough. Okay? It's okay. It's the fun of it. This is the Fourier transform. This is the plot of the Fourier series. Here's my omega c, and those are all my harmonics. And so you can see what's this is a very classic Fourier picture. Let's see. This is my last slide, and I'd like you to go back and pull this up and take a look at it with a couple of friends and talk about it. The last slide is just here's where the zeros happen for J1, J2, J3, J4, J5.